So we are going to look at when we take measurements in everyday language. The terms accuracy and precision get thrown about interchangeably. However, in science, they mean two different things. Accuracy refers to a measure of how close a measurement is to the target number, or like the bullseye. Sometimes we call that the accepted value of the quantity being measured. So last week when we talked about densities, how each substance has a specific density. In a lab, if you're trying to figure out the density of an item, if your answer is relatively close to the accepted value, or the one you look up for the density of gold or copper, there was that table of them, that would talk about the accuracy. Precision is the measure of how close a series of measurements are to one another. So this would be if you calculated the density of that object 3 different times, you took the volume 3 different times, you took the mass 3 different times, and then did the formula, the mass over volume, and you got 3 different densities. Looking at all 3 of those measurements, how close are they to each other? So looking at the little targets below here, the first one, there's the 3 darts on it. Side note, I play on a dart league, so if this doesn't make sense to you, you all understand you aim for the bullseye for darts, right? Okay, so this first one, all 3 darts, they're not close to one another, and they are not close to the bullseye. So this one shows you an example of not being precise or accurate. So this one would be an example of neither. Letter B here, they're all grouped way over here, but they're not on the bullseye. So they're not near that accepted value, so it's not accurate. However, it is precise because they're all 3 darts are close to one another. Does that make sense there? Okay. And then letter C, what are you thinking there? Accurate, precise, neither, one of the two? What do you think? Are they all relatively close to the bullseye? Yes, so I would call this accurate. Would you call it precise? Are the 3 darts close to one another? Probably not. One could make an argument it's not as precise as letter B, but it's still not as far off as letter A, so maybe you could argue it that way. What about letter D? Both. Good. And so we can do this with numbers too. So if the accepted value for a density of an object is 8.21 grams over milliliters, if you had 3 measurements and one was 8.19 grams over milliliters, one was 8.2 grams over milliliters, and one was another 8.2 grams over milliliters, would that be accurate, precise, neither, both, one of the two? So looking at these 3 numbers, are all 3 of them close to one another? Yep, so since all 3 are close to one another, they are definitely precise. And then are they all relatively close to the target number here? Yes, so then they'd also be accurate. Does that make sense? How we can look at it in terms of numbers, not just a bullseye? Okay, good. Percent error. This is probably the most practical page and most usable page that you will see in today's notes. The percent error looks at the ratio of what the value you got in the lab or in an experiment is as close to the accepted value. So the accepted value is the true or correct value based on general agreement with a reliable reference. So this would be, you usually have to look this up. You need some kind of research for this. And then the experimental value is the value that is measured during the actual experiment. So sometimes it is worth thinking of the accepted value as like the bullseye or the goal value you want in the experiment. The experimental value will be based off of the scientist's measurements or what he or she does in the actual lab. So when you are a human, it's very easy to make measurement errors. And so we look at the error is the difference between the experimental and the accepted values. So that would be this little formula right here. It's just a quick subtraction. More beneficial, however, is looking at the percent error. And this would be the absolute value of the error divided by the accepted value multiplied by 100%. So you pretty much take your error, divide it by your accepted value, and multiply it by 100 to get a percentage. And the smaller your percentage is here, the closer to the right or accepted value your answer is. So usually a percent error of less than 5% is good. Anything greater than 5 is concerning. So, for example, if we're looking at the density of aluminum at 2.7 grams over centimeters cubed, and a student calculated the value of aluminum to be 2.45 grams over centimeters cubed, they want us to calculate the percent error. So, percent error equals your experimental minus your accepted over your accepted times 100. So in this case, which one of these is our experimental value? The 2.7 or the 2.45?
2.45.
The 2.45 minus the accepted value is 2.7 all over 2.7, and then we'll multiply it by 100. And so remember in the numerator to take the absolute value just to turn it into a positive number. So 2.45 minus 2.7 is 0.25 over 2.7. And that equals 0.09. And then times 100 gives us 9%. So we were within, or this student was within 9% of the correct value. So that's semi-decent, pretty good. Make sense? Questions on the math at all, or good to go? Perfect. All right, significant figures. This is really the part that is only used, I would say, by like hardcore research scientists. And so there's always some uncertainty or error in any kind of measurements, whether it's due to human error or whether it's due to how precise your measurement device is. And so this whole concept of significant figures kind of takes each of those into account. So we're looking at uncertainty due to human error. Not just human error, but human skills. If you ask a first grader to measure the length of a line versus a high school senior, you're going to get two different answers. And then we're looking at the quality of the tool. So here ruler A has many more markings on it. So just by that nature, you're going to get a more accurate measurement than with ruler B. So you'd have to estimate this length on ruler B because there's no set marking. Whereas here, the line still falls in between two marks, but you know for sure that it's 2.5 centimeters. Does that make sense? And then you can estimate this third spot. So 2.5, maybe you feel like it's 2.54. So a lot of times they say that this last digit is uncertain because we had to estimate it. Whereas down here, we know for sure that it's 2, but we have to estimate this last digit down here. Does that make sense? So we've increased our number of certain digits going from B to A. So by definition, significant figures are all of the certain digits in that measurement plus one uncertain or estimated digit. Nope, digit's already there. Incorrectly reported measurements, the last digit is significant, however, it is not certain. So there are 5 rules that help you determine how many significant figures are in a number. So the first rule is that all non-zero numbers are significant. So if you look at example A, it says 237 has 3 significant figures because there are no zeros, so they are all significant. Example B has 1.897, and again, since there's no zeros, there would be 4 significant figures. Each digit would be counted as significant. Zeros that appear between other non-zero digits are always significant. So in the example of the 39,004, these 2 zeros are sandwiched in between non-zeros, so that makes them significant for a total of 5 sig figs here. 5.02, also this 0 is sandwiched in between 2 non-zeros, so that gives us a total of 3 significant figures. Each one of these counts as a significant number. Rule number 3 is that zeros that appear in front of all non-zero digits are called left-end zeros. Left-end zeros are never significant. So 0.008, the basic rule here is significant figures don't start until you have a non-zero number. So anything after that non-zero number would be significant. However, in this case, we only have the 8, so there would only be that one significant figure. In the number 0.000416, if you start at that first significant figure and head right, all of these zeros are not significant. So in this number, there would only be 3 significant figures. Rule number 4 says zeros that appear after all non-zero digits are called right-end zeros. Right-end zeros in a number that lacks a decimal point are not significant. So 140, again, we can start at the first non-zero and go right, but since there's no decimal point here, we cannot count that 0. So this 140 has only 2 significant figures. What's the other example? 75,210. Again, you can start at the first non-zero. When we get to this 0, you have to check for a decimal point. Since there is not a decimal point, that 0 cannot count. So then there would only be 4 significant figures here. Looking at the last rule, right-end zeros in a number with a decimal point are significant. This is true whether the zeros occur before or after the decimal place. So 620.0, you start with the first non-zero number, go right. Since there's a decimal place, both these 2 zeros will count towards significant figures. And so that would be a total of 4 significant figures.
Some of us have to go to cross country.
Good luck. And let's see, the last one here, 19,000, and they put the decimal point. So start at the first non-zero, go all the way to the right. Since there's a decimal point, all of these numbers count towards significant figures, and there would be 5. Let's practice. So, in 19.5, how many significant figures are there? 3. 0.0051, 2, just these 2. 204.80, 4 or 5? 4. This 0 doesn't count. What? Good? Okay. How about here with the scientific notation? 1.90. 2? Good. 14 beakers. 0. In items that are counted and not measured, you cannot have significant figures. Okay? So if it's just a random object as the unit, it cannot have significant figures. I know there's one in the assignment that pulls that on you too. Okay? It can only be a measured value. And then lastly, 700 kilograms. Just 1. How about now? 3. All right, last part is then significant figures and math, more specifically just the arithmetic. The results of the calculated answer cannot be more precise than the least precise measurement from which it was calculated. So that means your answer cannot have any more sig figs than your least or lowest number of sig figs in the problem. So here are the 2 rules. For adding and subtracting, the answer should be rounded to the same number of decimal places as the measurement with the lower or lowest number of decimal places. And then multiplying and dividing, the answer should be rounded to the same number of sig figs as the measurement with the lowest number of sig figs. So adding and subtracting is looking at the number of decimal places, whereas multiplying and dividing is looking for the correct number of sig figs. That's the big difference between the 2. And in each case, you're looking for the fewest decimal places or fewest sig figs. So our next slide here allows us to practice this. So with multiplying and dividing, are we looking at decimal places or sig figs? Sig figs. So this first number, 0.048, has how many sig figs in it?
6.
Just the 0.048? Start at your first non-zero and go right. So these zeros don't count, so we only have 2 sig figs. How about in the 32.97? How many sig figs? 4. So how many significant figures can your answer have? It has to be the lowest number, so your answer can only have 2. So when you multiply it out, your full answer here is 1.58256. So what would be your final answer? Two sig figs. So start at the 1 and then go to the 5. That would be 2 places, right? So is your answer going to be 1.5 or is it going to be 1.6? What is it?
1.6.
1.6 because of this 8. 8 makes it round up to 6. Okay? So then, were there questions on that at all?
What would the label be still?
It would actually be meters squared. Because you have a meters times the meters. Good question. Okay, so for the next example, it's a subtraction. So are we worried about sig figs or decimal places? Decimal places. So here we have 1 place after the decimal, and here we have 3. How many places after the decimal can our answer have? The low number or the high number? Pardon?
1.
1. You have to always pick the lowest number. So when you do the subtraction, you get 2.483. So what would our answer be in this case?
2.5.
2.5, yes. Grams. All right, looking at the next example, we have 14,570 divided by 5.81. Sig figs or decimal places? Sig figs, good. And so how many sig figs can our answer have? 3 right here. So when we do that, 14,570 divided by 5.81, we get 2,507.7456 or 266. So what will our answer be here? Do we need to worry about the decimals? No, we can't go that far. So we know we need the 2 and the 5. But if we keep it as this, that gives us 4 sig figs, correct?
So there's 2,500 and no decimal point?
No, because we still need 3. And if we did 2,500 with no decimal point, that only is 2. But you're on the right track. So we have to keep the 25, but then what would this 7 make the 0 round up to?
1.
A 1, and then we can put a 0 in that 1 spot and get kilograms over liters. See what I mean? It's a little messed up. Because I feel like this whole decimal is a lot better of an answer, closer to the more accurate one. But so that's why when I do labs, I don't use these. All right, how about 71.2 plus 90? Decimals or sig figs?
Decimal.
Decimals. So how many places after the decimal can we have? 1. No, try again. 0. So our answer here is 161.2. So our final answer would just be 161. Pretty much just drop the decimal. If this decimal had been 5 or bigger, we would have rounded that 1 up to a 2 for our final answer. So standard rounding rules still apply.